Hello, everyone, and thank you very much for the invitation. And today I will talk about the global plastic pollution crisis and the role of deepwater sedimentology. I believe and also hope that we can all agree that we are facing a global plastic pollution crisis. Since the 1950s, we produce millions of tons of plastic each year. In 2017 alone, 438 million tons of plastic were produced. And the prediction that there will be an exponential increase of plastic production over the coming decades. Plastic is an amazing material with unique material properties in various areas of application. But unfortunately, quite a lot of plastic is used for single-use throwaway products. 35%, for example, is used for packaging. And this is no surprise. Consumers have been educated over decades to view plastics as easy-to-use throwaway products. And all this resulted in the accumulation of 9,200 million tons of plastic in total. 2/3 of the produced plastics, 5,300 million tons, is now turned into plastic waste. It's been estimated that 39 million tons of plastic entered the environment only in 2020. This graph here shows the estimated plastic pollution in million tons per year over the coming decades under different scenarios. And if we continue with business as usual, this is indicated with this red line here, the annual plastic pollution will increase to 80 million tons per year by 2040. Even with immediate and concerted action, so if we keep pollution at a constant level, or if we even decrease it, we may still accumulate 710 million tons of plastic waste in the environment by 2040. And this is very concerning, because there's growing evidence for ecological harm from plastics. In the environment, plastics typically break down into smaller pieces, which increases the overall surface area and potentially benefit the release of toxins. And this may result in a peak of toxic release in the future. And as a result, there might be widespread ecological risk coming from plastics in the next century. And again, this is hugely concerning because plastics are widely dispersed in the natural environment. Plastic is present in the oceans. We can find it in deserts. And microplastic fibers were even found in snow near the peak of Mount Everest. But for now, I would like to focus on plastics in the marine environment. Rivers are likely to be the main pathway for plastics into the oceans. However, there's also plastic input coming from shorelines or from ocean transport. It's been estimated that roughly 10 million tons, give or take, of plastic enter the oceans each year. We now estimate that more than 5 trillion pieces of plastics are afloat in the world's ocean. And these floating plastics accumulate in the subtropical gyres, forming the 5 garbage patches. This seems like a lot of plastic, but apparently it only accounts for 250,000 tons. Remember that roughly 10 million tons of plastics enter the ocean each year, so only a fraction of the ocean plastic is afloat. If you crunch these numbers, you will find out that 99% of the ocean's plastics are missing. We don't know where it is. It's been suggested that most of the missing plastics are stored in deep water sediments. And this leads me to the second part of my presentation, where I want to talk about plastics and deepwater sedimentology. And I would like to address 2 points here. First, can deepwater sedimentology contribute to solve the global plastic pollution crisis? And second, could we use plastics in the study of deepwater sediments? So basically, could plastics help to better understand sedimentary processes in the deep sea? I think it is unlikely that deepwater sedimentology will help to prevent plastic pollution. We don't look at the source of plastic pollution, we look at the sink of all the plastics. And what we can do is we can identify and specify the scale and impacts of deep marine plastic pollution. So let's see what we know about deep marine plastic pollution. There's only a very limited number of studies available looking at plastics in the deep sea. But from the studies we have, we know that there are microplastics on the seabed. It is still very difficult to estimate microplastic concentrations across different marine environments. This early paper by Pham et al. Found highest concentrations to be in submarine canyons, with concentrations of up to 1,000 plastic pieces per square kilometer. However, more recent research actually indicates that these numbers might be much higher, more in the order of tens of thousands of pieces per square kilometer. And in addition to these microplastics which are sitting on the seabed, we can find microplastics in the sediments. So microplastics are plastic particles or fibers which are less than 5 millimeters in size. Typical concentrations of microplastics found in deep marine sediments varies between 0 to 4,500 particles per kilogram of sediment. Also for microplastics, it is difficult to estimate the magnitude of pollution across different marine environments. Again, mainly due to the lack of studies. However, initial studies indicate that concentrations are highest in submarine canyons, in trenches, and in contourite drift deposits. In summary, deep marine sediments may likely present a terminal sink for the ocean plastics. However, there's still only limited information available, and we have a quite blurry picture on seafloor plastic distribution. Highest concentrations appear to be in submarine canyons and channels, in ocean trenches, and in drift deposits. Now to come back to my first point, what can future deepwater sedimentology deliver to solve the plastic problem? Well, I think we could help to understand transport patterns and the dispersal of plastics across the seafloor. This would also mean to estimate seafloor plastic budgets and to find out how much of the missing plastic actually made it to the seafloor. Further, this includes to identify plastic accumulation hotspots and associated ecological risks. And finally, find out about the fate of deep marine plastics. Are they buried in sediments? How do they deteriorate on the seafloor? Basically the question, what happens with all this litter over the coming decades? And how quickly could polluted environments recover? And this could help to develop effective strategies to prevent plastic from reaching the deep sea. We could answer the question, what are typical plastic concentrations in certain marine environments? And would it make sense to define specific upper limit values? This could guide legislation and may also guide decisions on which areas we want to declare as marine protected areas. In the last part of my presentation, I would like to share some ideas with you how we could use plastics in the study of deepwater sediments. Could we use plastics or polymers as stratigraphic marker? The first plastic was synthesized in 1907 by Leo Baekeland. He called his invention bakelite, a plastic polymer which you might know from old telephones. Since then, several other polymers have been developed and produced. And the basic idea now is that the abundance or absence of specific polymers in the sediment could provide the maximum deposition age. Here, the maximum deposition ages of floodplain sediments were determined by different plastic polymers. The lowermost sediments were free-form plastics, suggesting an age older than the 1950s. In the overlying sediments, however, different polymer types were present, and the maximum deposition age could be associated with the development and production of these polymers. This method might also be useful to determine the maximum deposition age of deepwater sediments. Sadly, though, it only works because of the wide dispersal of plastics in the environment. Another idea is to use plastics as a unique tracer with the opportunity to learn more about deep marine sediment transport and pathways. A nice example about the main concept of this idea is the story about the friendly floaties. In 1992, a cargo ship in the North Pacific lost a container with more than 28,000 rubber ducks, which started a years-long journey across the world's oceans. Eventually, and sometimes after years at sea, the ducks washed up on coasts. And the distribution and timing of the reappearance of the ducks provided a way to monitor ocean currents. Could similar approaches be used in future deep marine sedimentology? Could we potentially link specific plastic items or polymers to a certain source to understand source-to-sink pathways? Different plastics have different hydrodynamic behavior due to their variations in shape and density. The abundance and distribution of certain types of plastics could provide information on sediment transport processes. Song and Peng, for example, use microplastic litter piles to reconstruct flow pathways in a submarine canyon. Similar, can the study of the transport and deposition of different plastics by sediment flows also provide information about fundamental physics of these flows? I'm afraid that this is all I can squeeze into 10 minutes. Nevertheless, I hope my presentation provided some food for thought and that you enjoyed it. Thank you very much for your attention, and I'm looking forward to the discussion.